Hello, hello, welcome back. Next problem is number 8, binary search. So, this one says it's easy, but this is actually the foundation of a lot of thinking that's going to help you with life and LeetCode. So, given an array of integers nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index, otherwise return -1. You must write an algorithm with O log n runtime complexity. So, example 1, you have an input here, and you have some numbers, and you have a target 9. Output is 4. Is 4 the index? 0, 1, 2, 3, 4. Yeah, so 4 is the index. So we got to return the index. And example is 2. So the target is 2. There's no 2 here. So the output is -1. Okay, so how do I think about these problems? Well, there's a couple ways to think about it. So if I imagine that I've never seen this problem before, part of what I would think about is the dynamics of the numbers in a number line, right? So what numbers do we have available? We have -1, 2, 3, 5, 9, 12. And you'd imagine if we had an accurate number line, it would be zeros right here, -1 is here. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, right, this goes infinitely, negative and positive. And you'd imagine if you do regular array iteration, so let's take this, I'll make it green so it's easier to see that it's different. Array iteration requires a for loop across every element. So you look at the -1, and what's the target here? Is that 9? No. Is this 9? No. Is this 9? No. Is this one? No. Is this one? No. So because you know that, and obviously not all of these are elements, so here, let me make the elements that exist blue. So 9, 12, these are blue. So you'd go from here to the -1, then you'd go to the 0, and then to the 3, to the 5, to the 9, and you'd find that, hey, we do have a 9. So that's good, right? So what does that runtime? It's O of n, because if it was the last number, we'd have to traverse the entire array to get to that last number, right? Well, let me ask you, what would happen if I dropped you at a random element into the array? Let's say I dropped you at the 7, right? Would you know which direction to go if you were looking for a 9? You might, right? There's a chance you might, because you know that there is a certain direction to all the numbers here. So if this is the same number line on the XY axis, and we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you would feel, at least if you were physically dropped on a hill, and if you were physically dropped on a hill and you were dropped at that 7, you would have some sense of what is up and what is down, right? And that is similar to how we're going to approach this problem, right? Except we're going to consider that instead of dropping you in a random place, we're going to drop you at the exact middle or close to the middle of the array, right? Because if I drop you too close to the middle of the array, or the middle, depends if there's an odd or even number of elements, then you know in your own mind, should I look left because it's larger than, or should I look right? So is 9 larger than 5? Yes. So I know that everything in here is not going to contain my 9 because this is a sorted array, right? And maybe this will make it clear. If I make 2 of these here, consider these green arrows now the bounds of what I'm looking at, right? So in the beginning, the bounds of what I'm looking at is the whole thing. And the middle, let's say, is the 5. And if 9 is larger than the 5, then I know that everything here is smaller and therefore not where my target is. Where my target is me closing the bounds and making it smaller. So now this is the bounds, right? This is the space and where the 9 could live. And the exact middle here is maybe the 8. 9 is larger than the 8 still, so I further close the bounds, right? I further make the bounds of where I'm searching a little bit smaller, right? And I keep doing this until I find it. And what is the maximum number of steps that this could take, right? Well, it depends on how many elements there are. But in terms of runtime complexity, because I'm splitting this space in half every time, I can only split it so much. And that so much is log n, right? I can only split this space in half so many times until I either get to the 9 or I get to the point where my bounds actually overlap and, you know, my search is over. So when we're coding, we have to think about these bounds as variables, right? Let's say I have a left pointer here and a right pointer here in the array, and I have a middle point. Let's just call it the 5 for now. I have a middle point, and I'm going to write this down. So left starts at, let's say, 0. Right starts at the last index, right? And that's probably the length of this array minus 1. And the middle is left plus right divided by 2. But imagine if you had 9 elements. You don't want this to be 4.5. You're either going to have to take the floor or the ceiling of this number. And I think practically it doesn't matter, but it can introduce a subtle bug depending on what you choose. Let's just choose the floor for now. All right, so just get rid of this. We don't really need this anymore. So the left starts at 0, the right starts at that last element, and the middle is this current bounds. And how are we going to do iteration? Well, we're either going to move the left or we're going to move the right pointer, right? And what point does that exit? Well, if the left overtakes the right, so as long as the left is smaller than the right, we're going to go into this while loop and consider what's going on. So I'm going to put this middle actually into the while loop. And let's think about the 2 conditions, right? So condition 1 and condition 2. Well, I could just write the code. In condition 1, our target, or let's say our middle, is smaller than the target. Well, let's check if the middle is the target. Let's say we're looking for the 5. If we're looking for the 5 and the middle is the 5, we could just stop completely, right? So if the middle is the target, well, then we're done, right? We just return some value. I think it's the index. So we return the middle index, right? We don't return the middle value, but we return the middle index, right? So if the middle is the target, we return the middle index. If the middle is, let's say it's larger than the target. So if the middle is larger than the target, let's say the target is a 3 or a 0 or a 2 or something, and we're at the 5, then we want to move the boundary, the right boundary over, right? So the right equals this middle index. All right, else we want to move the left one. The left is the middle index, right? So we're going to shrink this space until we find it, right? And in the best case, so in the best possible case, the target is just right in the middle of the array. Perfect, right? In a normal case, we're probably going to have to do some iteration. We're probably going to have to move these bounds, and we're going to have to look for, you know, the final position. So let's think about the edge cases, the cases where it gets really weird. So let's think about this case. We accidentally came to this click case, but it's good. So let's think about a case where there's 4 elements. The pointer is left, right, and the middle is here. And does our code work if the answer is either here, 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 or here? So does our code work if the answer is, let's say, in this position? Well, yes, because the middle matches it. Does our code work if it's in this position? Well, we're going to find that the target is larger, so the middle is smaller, so the left position moves up, so it's going to move to here, and then the middle becomes here. So it does work. It works perfectly fine. Does the code work if it's actually this right position? This is where the target is. Well, we'll find that the middle is smaller, so we'll move the left here, and this will be the new middle. And then we'll find that the target is still smaller, so we'll move the left here. And in fact, this will still be the middle, right? And then we'll find that the middle is still smaller. So what happens when the middle is smaller? Well, we're going to have to move the left. So now the left and the right are equal. They're the same thing. But then the middle will also be the same. So then we'll actually find it. Perfect. So in this case, it works as well. Let's go back. What happens in the case that it is this position? You know, it should be similar, right? It's smaller, so this becomes here, the middle becomes here, and then we find it. Okay, so in the case where there's 4 left, it works. What about the case when there's 3 left? And I think we can mentally, maybe we'll just do this one faster. You know, in the case where it's 3 left, if it's in the middle, it obviously works. If it's on the right side, then this won't match. This gets pushed up. This gets pushed up. And then these get all put in the same row. Okay, perfect. So works for that. And then if it's on this left side, the middle, it's obviously smaller, so the boundary gets pushed up. And then this becomes middle, and then we find it. Okay, so it works when there's 4, and it works when there's 3. So we've walked through the cases where, you know, you would think that they're edge cases, and it looks like, at least visually here, we may have a fix. So let's write some of the code for it, right? So you have a left, right? The left index, which is equal to 0. We have a right index, and that's the length of these nums minus 1. Perfect. So while the left is smaller than the right, we're going to do some checks. Let's make sure we have a colon here. And the middle is the floor of the left plus the right divided by 2. Now, can we do floor in Python like that? Maybe. We might have to import the math package, but let's just move forward. So if the middle equals, so this is the middle index, to be clear. And left and right, let's just always assume that's the index. So that's the middle index, and the middle value, let's just make that different, is the nums at the middle index. So if the middle value equals our target, then we can go ahead and just return the middle index. Else if the middle value is larger than the target, then we want to move that right index and we'll make that the middle index. Else we'll move the left index and we'll make that the middle index. Right, and then so what helps us exit out of this? Let's think about that case. What happens in that situation where they all end up in the same column? Well, actually, let's check the code. Yeah, so what happens in the situation where they all end up in the same column? This while loop actually does not work in that case. So what we have to do is let's keep something here first. Found middle index, or found target index, equals -1. And because we're not handling the case where the left, right, and the middle are the same value, then let's keep this while loop going as long as the left is smaller than or equal to the right, right? And we'll have this middle index here. We'll have this middle value here. And let's special case this where if the left index equals the right index and the right index equals the middle index, then they're all equal, right? So if the middle value is equal to the target, then we want to, return. Else, we want to break out of this while loop, right? So this is the case where we break out, where there's nothing more to traverse. And here at the bottom is the case where it's a regular case, where there is more traversal to be done. So we're reassigning left and we're reassigning right. Okay. So is there a case where this is stuck in an infinite loop? Let's look at that case. Let's think about it. So if the middle value is equal to the target, we return. If the middle value is smaller than the target, so let's say we have all these numbers and the target is 100, right? We keep moving. This keeps moving. And it moves until here. And ooh, yeah, I found the bug here, right? So if this was an M, if this was middle, and this was left, and this was right, then left will keep trying to be equal to the middle, but it's already the, we're stuck. So we're stuck in this case, actually. So we're stuck when the left and the middle are at 11, the right is at 12, the target is at 100, and it's just beyond. So how do we find that situation? One thing we could do is just, if the target is larger than the largest value, we could just return. That's one thing we could do. It gets us out of that situation because it's the same situation on both sides, right? Now, is that the permanent fix? So let's think about the situation on the other side. So if this is a this is the left, this is the right, and the target is negative 1000, right? Well, oh yeah, no, it actually works in this case because we're taking the floor, right? So the right will be coaxed to go to all line up, whereas the left will not be. And the left would be if we're taking the ceiling. So yeah, that's an interesting problem. Okay, so let's see. How do we do that? So I guess there's a couple optimizations here. So if the length of nums is 0, let's just return -1, return out of it. So here we assume that the length of nums has at least one element. So if it has that one element, then this right one will be the largest, right? So the largest value. So, you know, if target is larger than the largest value, just return -1. So target is larger than the nums at right, return -1. I don't know if I need this variable. Okay, so that helps fix one of the edge cases. Okay, cool. So if left equals right, we're going to get that middle value. And then if these are all three of these are equal, then we're going to do the check. And if not, we're going to break. I guess if not, we could return -1. And then if it is equal here, we return, or else we continue. Okay, so I mean, it looks like no matter what, we should be able to exit out of this while loop. I guess, what if we're looking for something in between? There's a, let's say we're looking for an 11, right? The target's 11. This is left. This is right. The medium becomes here. And the 10 and the 12 are here. And because of our code, we're going to want to move L to the middle. But the middle is already, I don't know if you can see this, I'll make this red. The middle is already equal to L, so the move doesn't do anything. Interesting. What if there's no more spaces to move, right? So imagine if this had a 9, 8, 7, and this started at the 7. This was the middle. Well, this moves to here, and this becomes the middle. And then, you know, 11's larger than 10, so the left moves to here. This stays the middle. And at this point, okay, so we need, it feels like the cases that we are getting stuck on is like when the left and the middle are actually right next to each other. When the left and the middle are right next to each other, there's actually nowhere to go when the target is larger. So here, actually, if left equals right -1, there's actually nowhere to move, right? If left equals right -1, this is the end. The left doesn't move anywhere else if the target is larger than the middle value. So this would be the end. It seems like. Seems like that would be the case. Okay, so list indice must be integers or slices, not float. Smart. Okay, so that was accepted. Is there another corner case I haven't thought of? You know, there's probably a clearer way to do binary search. So here the target was 5. And oh, that's funny. Yeah, so you know, there's a lot of edge cases here. Like if I'm looking for the 12, then I want to check that too, right? Wow. No, this one is, because I've done this floor, it's put me in a very peculiar place. I wonder what the method would be without this floor. Interesting. You know, this fixes it for that one case, but it could, easily another case could come up. Okay, so this is binary search. It's not the prettiest. It's definitely not the prettiest. I have a lot of case checks here, right? I think I can make this prettier. But hey, if there's only 3 items, I mean, it only adds a constant time check. So this should only happen in this case. Else this should happen. Hey, runtime, I beat 99.16% of users. Well, there's that. I still don't love how elegant this is. It's not the most elegant code. Like this check is not super the best, but I went from whatever it was to 99. I think I was like 20. All right, thanks a lot for stopping by.